Okay, so for unit 3 here, it's kind of a short unit. Okay, I just kind of finished the exam yesterday, putting it together for you. And I think if you prepare well for this test, it is a huge opportunity for you to raise your marks significantly. Okay, especially if your previous exams maybe haven't been where you would have liked them. Okay, I made the key the other day and it only took me 16 minutes, which I almost went back and changed some things, and then I had a soft spot and said, I'll let them have this test that's maybe a little more in their favor than the other ones have been. So if you prepare well for this test, there is no reason not to do very, very well on it. Okay, you guys did really well on your circular motion assignments, which, by the way, I'll pass back to you today. Okay, as well as I think you guys were doing okay. It looks like it anyway on the gravitation assignment you were working on. So it's nothing different than those assignments. It's going to be the same kind of stuff. All right, first thing we went over in this unit, okay, uniform circular motion. We talked about how that is an object traveling at a constant speed, but a changing velocity. That's delta ing over there, if you're wondering what this is. Okay, that's delta ing, changing velocity, right? So it's traveling at a constant speed, but its velocity is changing. If its velocity is changing, it's accelerating. Okay, so we're talking how this is always going to be dealing with accelerated motion. We talked about how to use centripetal acceleration formulas. We talked about how we derived the centripetal force formula from that. Okay, and really that it's just mass times acceleration. It's really just Newton's second law. Okay, it's still vector sum of all the forces. Okay, all of that stuff still applies here. So that was kind of the stuff we talked about the first kind of 2 days of the unit. All right. That'll be mostly multiple choice stuff. Okay, the kind of understanding the principles of uniform circular motion will definitely be multiple choice. There could be some, example questions about, something's being whirled around in a circle and the string breaks. What's it going to do? Okay, if something's going to move in a circle, what does it have to do? What has to be present? Things like that could be in the multiple choice. Okay, just checking your basic understanding of the concepts. So I would say going over your notes for lesson 1 and lesson 2 would be a pretty good idea, because that's really kind of the bulk of the multiple choice, right? Okay, and then the second thing we went over, we talked about banked curves and unbanked curves. Okay, we talked about that second and the third day, right? So an unbanked curve, friction provides the centripetal force. Right, so you stay in the curve because there is sufficient friction to keep you from sliding out of it. Right, so friction acts as a centripetal force. Okay, so we would have that force of friction, which is normally mu times the normal force. Okay, becomes mu mg because the corner isn't banked. If it's not banked, then gravity and normal force are equal. Okay, so that's how we get to this formula here. Okay, did we have a lot of those questions? Did we do quite a few of those? Should you expect to see one on the unit exam? Okay. All right, and then after that, we talked about the other kind of curve, which are banked curves. And banked curves use some of our normal force to help push us back into the middle. So a banked curve is an inclined plane, right, where normal force is pushing out like this. Okay, and that means that this part here is gravity, right? When you put those two together, their vector sum is the centripetal force. We get a small amount of force directed back towards the middle of the circle, okay, that helps to keep us in that circle. All right, we also talked about in class how the reason for building banked curves is not to be able to negotiate them faster, but to be able to guarantee what? Yeah, guarantee that we can negotiate that corner safely regardless of the road conditions, because we can't always guarantee traction. Traction is based on friction. Okay, maybe the corner is, we've had a bunch of freezing rain and the corner is covered with completely frictionless ice. We can't depend on friction at all. Take it at the recommended speed and you'll negotiate it perfectly. All right, so that was the reasoning behind developing banked curves. Okay, this was kind of the science behind how they work. Probably a couple of multiple choice questions about the principles behind a bank curve, right? That's also in lesson 2. So I already told you, make sure you go over your notes from lessons 1 and 2. Right? Because like we said, the bulk of the multiple choice questions will be about that. Questions on bank curves? Okay, so remember the bank curve formula. Okay, we did derive that in class. You don't have to derive it, but it's on your formula sheet like that. The tan of the angle of bank is equal to v squared over r times g. Okay, and then we talked about artificial gravity. That was the day we watched all the Chris Hadfield videos and saw all the cool stuff that happens in zero gravity. And we talked about how artificial gravity can be generated in a spinning drum. Okay? In fact, you can even produce artificial gravity in a spinning drum on Earth, right? That's what the gravitron ride does, essentially. It just spins you really fast, and the force of the outside wall pushing you back towards the center can allow you to lift your feet, okay, even though you're in a gravity environment. All right, so artificial gravity is very simply generated by a spinning drum. Okay, that spinning drum spins. You want to leave it because of your inertia, but the base does not allow it. So you want to follow this arrow, a straight line. Okay, but the inside of the drum doesn't allow it, and it pushes you back towards the center. If we're truly making artificial gravity, then this force here would equal the force of gravity. Okay? It's actually normal force that's doing that, but we could make it so that it equaled numerically the force of gravity. Okay? So artificial gravity questions are always going to be Fc equals Fg, but this time it's little fg. So it's mv squared over r equals m times g. Right? We're not trying to use Newton's universal law of gravitation here. All right, so should you expect to have a space station problem on there? Okay, and then from there we went to vertical circular motion. Now, what's different about vertical circular motion than uniform circular motion? Right. At some points, the object moves faster than other points. In uniform circular motion, the speed is constant. Okay. In vertical circular motion, both the velocity and the speed are always changing because gravity is now involved. The bottom of the circle is where we move the fastest. Okay. The top of the circle is where we move the slowest. What is our general rule for solving all vertical circular motion problems? Fc equals forces in minus forces out. As long as we can remember that and draw our free body diagrams, we're good. Okay, so the situations we dealt with, okay, top of the vertical circle on the outside. Okay, if we go over the top of a vertical circle fast enough, what will happen to this force? What's Fn also called? It's over there. Somebody needs to say it. Apparent weight. If I go over this fast enough, I would be apparently weightless, right? It would become zero. That's what we saw with the OK Go video, okay, where they were doing the zero gravity trainer. Okay, we also talked about going under the top of a vertical circle, so on the inside of the loop. Okay, in that case, there are no forces out. All the forces are in. There is, however, a minimum speed that must be achieved in order for that to happen. Okay, at the minimum speed, what's the only force acting? If I go just fast enough to stay in the circle, do I push on the circle? So the circle doesn't push back. In that case, there would be no normal force. There would just be gravity. I'm essentially a projectile. So at the top of the circle, whether I'm going over it or under it, I can have a feeling of apparent weightlessness. Okay. All right, so what we got to remember here is that at the minimum speed, Fg equals Fc. It's still forces in minus forces out. It's just this is the only force this time. Okay. And the other spot we talked about was the bottom of the vertical loop, and that is where you will generally feel the most apparent weight or feel the heaviest, okay? Because gravity is trying to pull you out of the circle, your inertia wants you to move this way, okay? So a normal force pushes especially hard at the bottom, okay, making you feel extremely heavy, right? So just remember in general this rule, okay, and you can't go wrong. All right. How would I word a question if I wanted you to know that Fn equaled 3 mg? How would I write it in words? Connor? Right. I would say that they feel 3 times heavier than normal. Okay. They feel heavy 3 times heavier. Are they actually 3 times heavier? No. Okay. But they feel 3 times heavier. So that would mean Fg or Fn, sorry, is 3 mg. If we were talking about the bottom of the vertical circle, that would mean, okay, that Fc equals 3 mg minus mg, right? Forces in, 3 mg minus forces out, gravity, mg. So this would end up being Fc equals 2 mg, and you had a question just like that on your circular motion assignment. Okay. All right. Then we talked about universal gravitation, so that's Newton's universal law, even though Cavendish is the one who actually made it work with his torsion balance. Okay. There could be some questions in the multiple choice about Newton, Cavendish, and Kepler, okay, about their contributions. Okay. Easy to make a multiple choice question that says, which of the following would Kepler agree with? A, B, B and C, whatever, and then have the next question say, which of the previous 4 statements would Newton agree with, or which one was Newton's universal law of gravitation, okay, or something like that. So make sure you review what each of those 3 people did, okay, so that when you encounter a question like that, you're able to discern that was Kepler's idea, that was Cavendish's torsion balance, and that was Newton's idea with the cannon perched on top of the mountain or whatever. Okay. All right. The other thing to remember about universal gravitation. It's not of the large object on the small object. The attraction is mutual. Okay? And it's going to say that in basically every question involving universal gravitation. There is a mutual attractive force. There could be some multiple choice questions that word this in, let's say, a deceitful or tricky way to make sure that you are still understanding that the attraction is mutual, not of the big object on the small object. Right, so make sure you review that a little bit. That was lesson 10, I think. Okay. All right, we did a couple of questions just to do with this, but we incorporated FNet into it. Okay, we did the ones with the Earth, the Moon, and the Sun in various positions. Okay, you had one on your gravitation assignment yesterday that had the 4 masses, and you were trying to find the net force on one of the masses. Expect you're probably going to get a question about net gravitational force on the unit exam. Okay, probably not as complex as the 4 masses that you have on your assignment, but something that might be, here's 3 masses, determine the net force on the one in the middle or the one on the end, okay, or something like that. So expect you're going to see a question like that. And then naturally from there, we moved into, there you go. I forgot I had those diagrams on there. Okay, then we moved into satellite motion because satellite motion involves centripetal force equaling Newton's universal law of gravitation. So mv squared over r times g m1 m2 over r squared. Which m is on both sides? Mass of the satellite or mass of the body being orbited? Mass of the satellite. Important thing to remember. We don't want to cancel off the wrong mass. All right, remember, we had a perfect example of it on the quiz this morning. Okay, remember height, altitude, and surface. If they use those terms, you are either adding the Earth's radius on, or today you were subtracting it off. Right? But if they're talking about height, altitude, or above the surface, you know that in some way, shape, or form, the Earth's radius is going to be a number that's either added or subtracted somewhere along the way. All right, and today's question also involved having to do the substitution into FC. Okay, it is entirely possible you could get a question like that on your unit exam, or maybe I'll be a nice guy and maybe it'll just be mv squared over r, but you don't know. So you best know how to do both. Okay, and I mean, other than that, there's nothing tricky about a satellite motion question. It'll be something orbiting something else. Okay, and you guys can get it from there. All right. So we talked about that. That was substitution. And then the other day we talked about gravitational field strength. Okay, guys, the biggest thing with gravitational field strength on this unit exam is always that people just don't solve for gravitational field strength. They solve for force of gravity instead. Right? It's just a matter of making sure that you read the question carefully. Right? I'm sure you heard in the podcast there on Tuesday me like making a bet with my class saying I will bet that still 1/3 of you, even after I tell you this, will do it wrong. Okay? I've only had 2 classes ever prove me wrong on that. Okay? Your gravitational field strength question on your unit exam is going to have the words gravitational field strength in bold-faced italicized text. Okay? If you solve it as a force of gravity question, you are going to get absolutely nothing, okay, for that question. So make sure you read it carefully. All right. Okay, and then we got Kepler as well. There may be a problem on the exam that you could solve either with Kepler or with this. Okay, but which way always works? Does Kepler always work, or does FC equals FG always work? Well, hopefully you guys can figure that out by Tuesday or by Wednesday. Okay. All right, so go over it. Just make sure you know it. Make sure you know Kepler's laws. Okay, he only has 3 laws. Okay, law of elliptical orbits, law of equal areas, and then his law of periods. So make sure you can recognize those from a description, because again, that's good multiple choice question type material. All right. That might not be right. I think I made a mistake there. Hang on. There are 15 multiple choice. Let me call it up here. Okay, there are 7 written response. Yeah, only 7 and only 29 marks. Okay, and 15 multiple choice. This is by far the shortest unit exam that you have written for me. Okay, like hugely, really, really short. Okay, like I say, it only took me 16 minutes to make the key. All right, so time should definitely not be a factor. All right, especially if you're well prepared. What's that? Not at all. No, I'm not making that a challenge. Okay, do not try to finish the test as quickly as possible. Okay, you have an entire period to write it. Take the entire period to write it if you want. If you're done early and you just want to get it out of your hands, that's fine too. But okay, you want to take advantage because, like I said, this is a major opportunity to boost the exam portion of your mark if you are well prepared. If all you do over the next 6 days is not look at your physics, don't expect this exam to go well. Okay, it will reward those who are well prepared. It won't punish those who are poorly prepared so much as the other ones might have. Okay, but I'm not saying, oh, don't take it this way. Coder said the test is easy, so I don't have to study. Coder never said that. Okay, he unequivocally never said anything like that. He said this test will reward those who are well prepared. Okay, questions on any of that stuff? Anything you want me to go over? Types of questions you want reviewed? Okay. So if we want to find the net gravitational force, so let's say I've got, okay, these 3 objects in a row here. All right, let's say this one is 3 kilograms, this one's 4 kilograms, and this one is 5 kilograms. I want to find the net force on the 4 kilogram mass. This distance here is 0.2 meters, and this distance here is 0.6 meters. All right, I want to find the net gravitational force on the 4 kilogram mass. So the 4 kilogram mass is being pulled this direction and this direction. All right, so the two forces that I calculate are going to be the same or opposite? Opposite. They're pulling in opposite directions. So I'm going to go force of gravity 4.5. So between these two here. So that's going to be 6.67 times 10 to the minus 11 times 5 times 4 divided by 0.2 squared. Okay, so we got 3.35 times 10 to the negative 8 newtons. Okay, on this side, and then the other one. Okay, it's going to be 2.22 times 10 to the minus 9. All right, so we'll take our 3.35 and subtract the other one because they're opposite, so that's the sum of all forces. All right, so there's our answer. Our net force is 3.1 times 10. Actually, it would just be 3 because I only have one significant figure in this question. Okay, it would be 3 times 10 to the negative 8 newtons left or towards the 5 kilogram mass. Okay, so all I did here was calculate the two forces of gravity. Right, so I calculated force of gravity here, and then this one was okay, so I calculated both of those, and then I said F net equals FG 4.5 minus FG 3.4. Okay, so that was our 3.35 times 10 to the minus 8 minus 2.22 times 10 to the minus 9. Okay, and then I got our net force there. Michael. Yes, you would put them tail to head. Okay, other questions? Yes, you'll get that formula. It's on the formula sheet on the front of the test. Okay, so the bank curve formula will be on the test, yeah. Okay, any other questions? All right, in your circular motion workbook is the review package. Okay, so there's this little blurb here, which is essentially what we just did. Okay, it's kind of the stuff I wrote down there. And then there's a few suggestions. Okay, review all your notes. There's the formulas you're going to get on there. And then there's some review problems under that with the answers on there, so you can check and see if you're doing them right. Is your question? 3.07 times 10 to the negative 8? Yeah. All right, so that is what you guys should be working on for remainder of class, which is what, another 20 minutes or so. Okay, so you got some more time to review for your exam, maybe work on a few of these problems. Okay, something to keep in mind. I'm not here on Tuesday. So you can't see me for scheduled help on Tuesday because I won't be here. Okay, that was the reason I did the review today and not tomorrow. Right? At least today there's scheduled help. So if you want to come in and ask me some questions, you can do it today. Okay, you could possibly do it tomorrow after school as well. Before we have CLCs, I could answer a couple of questions then too if you had them. But I'm not here Tuesday because I'm at the track meet. Okay, so I won't be available to answer questions on Tuesday. Okay. All right, so have at her there, guys. Okay, so typical bank curve question will probably, it'll give you 3 of the 4 things, right? It'll give you gravity because it'll be on Earth, and it'll give you either radius and speed, or it'll give you radius and angle, right? So you'll be asked to calculate one of the things in this formula. Okay, so it would probably be worded something like, how fast can a 18-degree curve be negotiated if its radius is 200 meters? So it would give you this, and it would give you the angle and ask you to calculate v. So just be manipulating for v, right? Or it could say you have a bank curve that has an angle of 20 degrees, and a car can safely negotiate it at 40 meters per second. What's its radius? So you're solving for r. That's the only speed, because it would be a frictionless curve. There's only one speed you can take a frictionless bank curve at safely. It won't say max speed. At what speed can it be safely negotiated, is what it would say. Or it'll say the speed it is safely negotiated at is this, right? And then you calculate something else. Yeah, I'm not going to word it like that. I did that on a quiz once, and this will just be strictly a bank curve question. Yeah. No. I don't think so. I can't see myself asking like a bank curve question on another planet, right? Or same with vertical, like, yeah, I can't see myself doing that. Yeah. Hey, any other questions there, guys? Maximum speed. Okay, so if we're trying to find the maximum speed, we're going to multiply both sides by r times g. Okay, so we have the tan of 18 degrees, okay, times 120 times 9.81. Okay, the key here, and sometimes this happens, is people leave their calculator in radian mode. Oh, underneath. Okay, yeah. All right, so we just multiply those together, and we would have our actual answer, which I think was 19.6 meters per second, I think was the correct answer. Yeah, something like that. Okay.